All right, so this is the second video in AP Calculus BC on integration by parts, and we were at the point with the last example where we had to use integration by parts more than once in order to get our integral to a point where we could actually integrate it. So if many repetitions like that are going to be required, or even sometimes if it would just be one instance of using integration by parts, the calculations can become cumbersome. So sometimes you can use a method that's known as tabular integration. It's still the integration by parts process, but it's much simpler. But it can't always be used. It can only be used if one of the two functions being multiplied within your integral is eventually going to work its way down to a derivative of 0. So that's only going to happen with polynomial functions, like an x squared, for example. So here, if I use f of x equals x squared and then make g of x be the e to the x, we make a table. That's where the term tabular integration comes from. So the first column is you're going to start with your f of x function, and you are going to do all of its derivatives until you get all the way down to a derivative of 0. You have to do that column first, because in the right-hand column, you're going to integrate the g of x function. And you need to know how many times to integrate it. Well, you're going to integrate as many times as you had to take the derivative on the left. So that would be until we had 4 rows. Luckily, e to the x is easy to integrate. So then, here's the tricky part. This is what you do. You're going to make connections from the top row in F to the next row down in G, like so. Then you're going to put a positive, a negative, and a positive. And the signs always start that way, positive, negative, positive. Then we combine the products of those things together, does it down here, and we get the answer. So it would be positive x squared times e to the x minus 2x times what it's connected to, which is an e to the x, plus 2 times the e to the x that it's connected to, and then the plus c. And I'm going to click back to in the last video when we worked it out doing integration by parts multiple times. Look at what we got. So tabular integration got us the exact same answer. But I didn't have to remember the u times v minus the integral of v du, that whole formula. I could do it with tables like this. As long as I remember that the first column is my derivatives all the way down to 0, and the right-hand column is the same number of integrals as I did derivatives on the left. And then I alternate my signs, positive, negative, going on a diagonal of multiplying the things together. Super, super, super easy. So I want you to give example 4 a try using tabular integration. So pause this video, give it a try yourself, and then come back and check and see how you do. All right, so over there on the right-hand side in blue, you'll see what the final answer is, and you see I had to make the x cubed be the one I took the derivative of because it would eventually go to 0, and then I had to work back through my sine of x cycle to figure out all of my terms there. Okay, so now let's extend that into not just finding a general solution with the plus c at the end, but what if I wanted to actually find a particular solution? So here we have the differential equation dy dx equals x natural log of x with the initial condition of y equals -1 when x is equal to +1. We want to confirm the solution graphically by showing that it conforms to the slope field. So the slope field's down there, and we'll look at it in a minute. But I want to figure out what function would give me a derivative of x natural log of x and go through the point 1, -1. So if you're looking at that differential equation, x natural log of x, so we know we're going to need to integrate x natural log of x dx. And so you might immediately think, oh, x, if I take its derivative, I'll get a 1, and then its derivative would be a 0. So maybe I could use tabular. If you do that, though, then the ln of x would be in the column that you would have to integrate. If you know what the integral of ln of x is, I would love to hear from you, because none of y'all know what it is. So what that tells me is that because I can't integrate the other guy easily, I'm not going to be able to use tabular integration. I'm going to have to use my u and my dv and that sort of thing. So when I'm choosing what I want to be my u and my dv, I'm going to think about that thing that I was just discussing. If I make ln of x the dv portion, then I'm going to have to integrate it to figure out what v is. But again, I don't know how to integrate ln of x. So that means ln of x needs to be my u, and so x dx would be my dv. So du, the derivative of ln of x, is 1 over x dx, and the integral of x is 1/2 x squared. So that gives me u times v would be 1/2 x squared ln of x minus the integral of v times du. Now luckily, when I simplify what's in this integral, I'm going to pull the 1/2 out in front. X squared times 1 over x is just x. I can integrate x all day long. So that's 1/2 x squared ln of x minus 1/2 times 1/2 x squared plus c. So we get y equals 1/2 x squared ln of x minus 1/4 x squared plus c. So that would be our general solution. But then to get the particular solution, I want to substitute in the xy pair that I have. So that means that y is equal to -1 when x is +1. So we get -1 equals, all of this first piece is going to become 0 because it's got natural log of 1 in there. And then minus 1/4 plus c. So when we add the 1/4 over, we get -3/4 for our c value. So our function would be y equals 1/2 x squared ln of x minus 1/4 x squared minus 3/4. And so this problem really reiterates the fact that you can't always use tabular integration just because one of the pieces would eventually differentiate to 0. You got to pay attention to whether or not you can integrate the other piece as well. So this blue solution that I came up with, here's the slope field for dy dx equals x ln of x. The blue curve that's drawn on this slope field is the function 1/2 x squared ln of x minus 1/4 x squared minus 3/4. And here is the point 1, -1. All right, so let's try another one. E to the x cosine of x. Immediately I noticed that those two things, e to the x and cosine of x, neither one of them will eventually turn into 0 if I take the derivative long enough. So I have to do the formula. As far as what to choose, I'm going to make e to the x be my u, and I'm going to make dv be cosine x dx. So that makes du also e to the x, and v sine of x. So the integral of e to the x cosine of x dx, and you may be wondering why I chose that combination. You could have done it the other way. Feel free to try it the other way. See if we end up with the same thing. So I would do u times v minus the integral of v, oh, this thing's dx on du. Okay, so then you're looking at that, and you're like, the integral of e to the x sine of x. Can't really integrate that because it's still got the same issues that the e to the x cosine of x had. Okay, so let's try integration by parts with it. And let's use the same combination. This time it'll be sine of x dx for the dv though. So du is going to be e to the x dx, and v is going to be negative cosine of x. So that makes this the integral of e to the x cosine x dx equals e to the x sine of x minus this u times this v, so that would be negative e to the x cosine x minus the integral of this v times this du, so that would become a plus e to the x cosine x dx. So if I distribute my negative through, I get the integral of e to the x cosine x dx equals e to the x sine x plus, well, I'll keep it in blue, e to the x cosine x minus the integral of e to the x cosine x dx. And now you're thinking, geez, lady, now I got another integral that I still can't work with. But if you look at this integral right here, notice he is the exact same integral as what I've been trying to find since the very beginning of the problem. So let's use our algebra skills. Those are like terms, the things I've highlighted in purple there. So I can combine them together. Well, if I take the one on the right and move him to the left-hand side of the equal sign, I would add him to move him over. So that would become two integrals of e to the x cosine x dx are equal to e to the x sine of x plus e to the x cosine of x plus c, or one integral of e to the x cosine x dx is equal to 1/2 e to the x sine x plus e to the x cosine x plus c. And you can pull the plus c out because 1/2 times c is still just a value of c, but otherwise you could just leave it right like that. All right, so that's going to end our second video on integration by parts. I know there's some more examples to go through, so I am going to make a third video going through example 7 and example 8, where we can actually integrate a single function using integration by parts.